Hello. So this is another pretty long section. I apologize for that. That's just the way it's been designed. But we'll get through it. So today we're going to talk about describing and analyzing data. Displaying data in a clear and informative way is certainly an important and necessary step in research. Just as important is describing the data numerically, so that they can be compared and analyzed. The arithmetic mean is the sum of all the data values divided by the number of data points. The population mean is the sum of all the data values divided by the number of points. Okay, so here's the deal. The arithmetic mean is what you've always thought of as the average, where you add them all and divide by the number of data points you have, okay? The difference between the population mean and the sample mean is just what it says. The population mean is if you actually have all the data values for an entire population, then you would use the population mean, which is called mu, this little m thing here. If you are just finding the mean for a sample, then you use x bar. That's x with that little bar over it. It's the same thing. You're still finding the mean in the same way in both situations. It's just that there's a different symbol for each, okay? So example 1 says a sample of the number of sick days employees at Witt's insurance agency took last year is listed below. Calculate the mean of this sample data. And again, this is just a sample. It's not the entire population, so we're using X bar. And of course, just like with average, what you do is add them all up. And there's 8 data points there. So we get 71 divided by 8, or approximately 8.9. So the average amount of sick days took was about 9 days. The median of a data set is the middle value in an ordered array of the data. So basically, you put the data in order and then find the middle number, and that's the median. Unless there's an even set of numbers. And so we're going to look at an example of that right now. So it says a VO2 max score is the maximum amount of oxygen that one's body can transport and use during exercise. It's measured in liters of oxygen per minute. Given the following VO2 max scores for 12 women, find the median score. So we need to put these all in order. And as we order them, I'm going to mark them out. The smallest one is 23.0. And then the next is 25.5. Then we have 26.8, 26.97, 27.0, 27.1, 27.2, 27.52, 27.53. Oh, let me pause and rearrange this a bit so I can fit them all on one line. Okay, hopefully I can fit them all on here now. Then there's 27.53. We said 27.7. Oh, I missed one. Missed 26.94. So okay, got it. And then the last one is 28.3. Okay, So we're going to count and find the middle values. So let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There are 2 in the middle because it's an even set. So what we have to do is take 27 and 27.1 and divide by 2. We're going to find the average of the middle 2. 27.05 is our median. The mode is the value in the data set that occurs the most frequently. Find the mode of each of the following sets of data. State of the data set is unimodal, bimodal, multimodal, or has no mode. And you'll see what that means as we work these problems. So this one, I'm going to go ahead and tell you, the most used in here is violet. You can see it's used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times it looks like. So the mode is violet. And since it's the only one used the most, it is unimodal. There's only one mode. It's used 10 times and everybody else is used less than that. For the favorite football jersey number, we have that there are no values that are repeated at all. So there's actually no mode. Ages of children at the community playground one afternoon. Let's see. Here's a 4 used 3 times. And 7 is also used 3 times. So the modes are 4 and 7. So we would say that this is bimodal because there are 2 modes. And last, the number of ATM withdrawals per hour at the downtown branch of University Bank. 10 is used twice. 13 is used twice. 9 is used twice. And 14 is used twice. They're all used twice. So there is no mode. An outlier is a data value that is extreme compared with the rest of the data values in the set. Like if you have a set with 1, 4, 3, 6, 7, and then all of a sudden you have another value that's 100. Then 100 would be an outlier because it doesn't look like any of the others. Sometimes you'll use an outlier in your calculations and sometimes you won't. It just depends on what you're looking for. Given the following data set, find the mean, median, and mode, and decide which measure of center you think best describes the data. So the mean is, of course, all of these values added up. And there are 11 of them. So we get 411 divided by 11. So the mean is approximately 37.4. To find the mode, we need to list them all in order. Okay, so here's the order. I'm just going to tell you for time's sake. Okay? And there's an even number of them. So, let's see. 1, 2, 3, 4. 1, 2, 3, 4. 5. It ends up right there at 26. So the median is 26. And then the mode is the most used value if there is one. And the only one that's used more than once is 15. So the mode is 15. Now it asks us which measure of center should we use to describe the data. Basically, if there's not any outliers that you factored in, then the best measure is usually the mean. Okay, so the mean would be the best measure of center here, 37.4. The median just comes in too low between the lowest and highest values of 11 and 84. And the mode comes in way too low. Okay, so the mean is definitely the best measure of center here. The range is the difference between the largest and smallest values in the data set, which tells you the distance covered on the number line between the two extremes. Find the range of these sets of data. The number of students enrolled as computer science majors over the past 12 semesters. So the maximum out of here is 54, and the minimum is 5. So the range would be 54 minus 5, or 49. The number of shoppers at a gas station downtown Monday through Sunday, 1 week. The max is 1,054, and the min is 1,005. So the range would be 1,054 minus 1,005, or 49. And yes, it's just a coincidence that they're both the same. Okay, next is a biggie. We're going to talk about standard deviation. Standard deviation is a measure of how much we might expect a member of the data set to differ from the mean. So we have the mean, which is usually the best representation of the data. And we have this little range on either side of the mean that tells us where we expect most of the data to lie, okay? And that's the standard deviation. So the standard deviation for a population, notice it is different for a population in a sample. For a population, it's the square root of the sum, that's what that E thing is, of each data value minus the mean squared divided by the number of data values in the population. The only difference with the sample standard deviation is that we used n minus 1 on the bottom. So it's the number of data values in the sample minus 1. Now, to do this calculation, you can see it's quite complicated looking. And the fact that you have to use each data value minus the mean means that you can't just put the numbers into one calculation and get your answer. You have to go through a process. And we'll talk about how to do this process by hand and how to do it in Excel, because Excel will make it quite a bit faster. Example 6 says calculate the standard deviation for a sample of 9 ages of students working with a university theater production of Macbeth. So we have these 9 ages here. The first thing that we always do when figuring out the standard deviation is to find the mean. So we're going to add these up. Divide by 9, it said. And we get that the mean is 20.67. So we're going to be filling into our formula here. It's the square root of the sum. I like to be color-coded, you know. Of the square of each data value minus the mean divided by n minus 1. Well, it's easy for us to go ahead and figure out what n minus 1 is, because that would just be 9 minus 1. So on the bottom here, don't you love copy and paste? Or I do anyway, is 8. But the rest of it is a process. And we're going to use this table to walk us through the process. So what we do is we take each data value and we subtract the mean, which was 20.67. And when we do that, we get a number for each one. This first one is negative 3.67. The second one, when we subtract, we get 0.33. And we go through and we do this for the entire data set. So for the third one, we get negative 2.67. Again, we get negative 2.67. Then we have 3.33. Negative 1.67. 0.33. Negative 1.67. And 7.33. Okay. The next step is to take each of these differences here that we just found and square them. So the first one, when we take 3.67 times 3.67, we get 13.47. And then we'll do 0.33 squared and get 0.11. Then negative 2.67 squared is 7.13. And this one was the same. And I'm going to pause while I finish this up. Okay, so we're almost there. Got to finish filling in all my squares here, and I hope you're doing this on your paper too, so you'll have something to look back at. After we do that, we add them all up, all of these here, okay, to get 96.01. We're almost done. So here's what we had so far. And so what we need to do is put in our sum of 96.01 on top. Now all we've got to do is divide. And take the square root. So the standard deviation is 3.5 years. So what we can do is we expect that the age of the average student is about 3.5 years younger or older from the mean age of 20.67. Okay? And like I said, I'll add on how to do this same example on Excel to the end of this video. The next definition, the empirical rule. When the distribution of a set of data is approximately bell-shaped, we can estimate the percentage of data values that fall within a few standard deviations of the mean in the following way. Approximately 68% of all data points lie within one standard deviation above and below the mean. And by the way, if you choose to split this lesson in half, then I would stop just after the standard deviation and then pick up here. Just a hint. So the empirical rule says that approximately 95% of all data points lie within two standard deviations above or below the mean. So 68% lie between one standard deviation above and below the mean, 95% within two standard deviations, and 99.7%, almost all of the data, lies between three standard deviations of the mean. To understand this, let's look at an example. Suppose you suspect that the emergency room waiting times for a local hospital have a bell-shaped distribution, which is required for us to use the empirical rule. The data have reported a mean of 116.9 minutes and a standard deviation of 56.1 minutes. Identify the range of waiting times that 95% of patients are likely to experience. And I thought I had put a bell curve on here, so I'll pause and do that. Okay, so here's what we do. We'll put the mean in the middle, 116.9. Then each data value to the right will be 56.1 minutes greater. So 116.9 plus 56.1 is 173. Add another 56.1, you get 229.1. And add another 56.1, you get 285.2. Then going the other direction, 116.9 minus 56.1 is 60.8. Subtract 56.1 and you get 4.7. And subtract another 56.1, you get negative 51.4. It's highly unlikely we'd have negative minutes. That's not even possible. So obviously we're not going to be going down that far. Okay, so what it asks us is identify the range of waiting times that 95% of the patients are likely to experience. Okay, so 68% would be 1 standard deviation from the mean. I know my picture's definitely not perfect here. Then 95% would be 2 standard deviations from the mean. So we can say that the wait time for 95% of patients is between 4.7 minutes and 229.1 minutes. Part B says estimate the percentage of patients that will wait less than 2 hours and 53 minutes. So first of all, our data is in minutes only. So we need to change 2 hours and 53 minutes. That would be 2 times 60 plus 53, or 173 minutes. So we want the percentage less than 173 minutes. And I found my picture. I've updated it. Okay, so we want, here's 173, and we want less than that. Now, we're not going to include down to the negative 51.4. So we're going to stop at 4.7 minutes. So this is what we want. We want that shaded region. So to figure this out, we know that from here to here is 68%. Actually, I looked at my picture wrong. We do go all the way down because we are talking less than. Okay. So we know there to there is 68%. So we can handle that. We also know, if we look at this a little bit different, that from here down is 50% of the data, right? So we just need to add on this little piece right here. That little piece would be half of 68%, or 34%. So if we add those two together, then we get that 84% would wait less than 2 hours and 53 minutes. Okay. Percentiles divide the data into 100 equal parts and tell you approximately what percentage of the data lies at or below a given value. So here's what percentiles look like. At the end is the low value. At the top is the high value. And in the middle is the median. All of these we've discussed so far. Then between the low value and the median is called your first percentile. And that is halfway between the in your data points, okay, the low value and the median. The median is called also your second percentile. And then the middle data point between the median and the high value is your third percentile. And the high value is the fourth. Okay? Sierra received her scores from taking a mathematics placement test for her chosen university. Choose the best explanation for what it means for her to be in the 61st percentile. Well, let me go ahead and tell you what it means to be in the 61st percentile. That means that you did better than 61% of your peers. It doesn't mean that you scored 61%, that you got 61% of the questions right. Okay? It means that Sierra scored better than 61% of her peers. So A says she correctly answered 61% of the answers on the test. We already said that's not the case because it's not a comparison. And percentile is a comparison. 61% of people taking the test scored the same as Sierra. No, she scored better. Percentiles, I have to write it down here, show the percent score below. I'm going to skip C. That's going to be our answer. D says Sierra missed 39% of the test questions. Again, not a comparison. So it can't be D. Sierra's score was at least as good as 61% of the people taking the test. Yes, she scored at least as good or better than 61% of the people taking the test. So we just talked about, I already drew this picture, the first quartile, 25% of the data is less than or equal to this value. The second is the median, and half of the data is less than or equal to this value. And the third is also the 75th, because it's 75% is less than or equal to this value. Example 9 said, on Carl's recent standardized test results, the picture graph of his score showed he was above the third quartile in language arts. His classmate Asher said his score was at the 70th percentile, while Riley said hers was at the 79th. Which of the three had the best language arts score? So, to put these in perspective, if his was in the third, if Carl's was in the third quartile, then he is above the 75th percentile. He scored at least better than 75% of his classmates. We don't know exactly how high he scored, but it was at least there. So we can see pretty easily that Carl scored better than Asher because Asher's was at the 70th. But Carl and Riley are both greater than the 75th percentile. We don't know exactly where Carl scored, if he was in the 80th, but we knew it was higher than 75, but we don't know exactly. Riley's was exactly the 79th. So we don't know if Riley or Carl scored better. Because both are above the 75th percentile. One more example. To receive federal financial aid for higher education, students must first complete a free application for federal student aid form, commonly called the FAFSA. A lot of you have probably done that. So have I. Given the following data gathered from FAFSA on the number of applicants by state, use Excel to find the minimum and maximum data values, mean, median, mode, range, and standard deviation for the data. So we've got this list, and I have included this list in Moodle for you so that you don't have to type all those in to Excel like I did. Okay? And so I'm going to stop here and pick up on the Excel example in just a moment. I told you I'd put this spreadsheet on Moodle, so it'll be below the 8.2 video, which is not done yet. And it's right here, the 8.3 example 10. And I'm just going to click on that. And I'm going to blow it up. Okay? So here's the data from example 10. And we're going to find each of these values. Now you're going to want to write down what I type in so that you'll know what to type in the future. Or you could save this and you can always click on the cell and see what was typed. But easiest thing to do is to write it down. So first we want to know the minimum. So to find the minimum, we type equals. You always start with an equals, M-I-N. For minimum. Then a parenthesis, and we want all the number values. So I'm just going to go and at the top start selecting and pull all the way down to the bottom. Okay? Close parentheses, hit equal, and the minimum out of there was 0. There was one college that didn't have any FAFSA applications. So to find the maximum, very similar, equals max, parentheses, and we're going to select all those data values again. Close, enter, there it is. The mean, you don't type mean, you actually type average. So equals average. Open parenthesis, select all the data, make sure you get it all, close, enter. So the mean is 21,611.48. For the median, type median, equals median, open parenthesis, select all the data, close, enter. For the mode, type mode, M-O-D-E, open parenthesis, select all the data, close parenthesis, enter. The range, we need to subtract for the range the maximum minus the minimum. So we're going to say equals, and then we're going to select the maximum value, subtract minus the minimum value, and hit equals. And obviously it's the same as the maximum because the minimum was 0, but that's how you do it. And the standard deviation. Define the standard deviation in Excel without having to go through the long process that we're going to do in a minute on Excel, which is easier than doing it by hand, is equals STDEV, open parenthesis, select all your data, close, enter. And so there's the standard deviation. So that's example 10 on how to find each of those things. If you didn't write them down, be sure and rewatch this little section and write them down. Now let's look over at number 6. We wanted to do this and show you what it looks like to do the table in Excel. And it is a lot simpler. Basically, find the mean first. So we'll say equals average, open parenthesis, and select our data points, close, enter. So there's the mean, just like it's 20.67, just like we found it on our paper. And then we want to take each data value and subtract off that mean. So we say equals the data value minus, and we can select down here, but we have to put a $sign first. Let's see. There we go. And the reason I'm doing that is so that when I drag this down, and it didn't keep it, let's just type it in. That'll be the easiest thing to do. 20.67. There we go. And now when I drag this down, it will subtract 20.67 from each of those data values. Now we want to square each of those. So equals, we got to put it in parentheses because some of them are negative. We're going to select this one here, close our parentheses, hat, that's above the 6, shift 6, 2. That'll square it. Hit enter and it's squared. If I pull it down, it'll square all of them. And then I want to find the sum down here. So we say equals sum, open parenthesis, and select these values because that's what we want the sum of. Close, enter. Just what we found before. And now for the standard deviation, we need to fit in our formula. Remember, it's the square root of the sum divided by n minus 1. I'm going to go ahead and go up here and put in n minus 1. We said that was 8. Okay? And so, well, I really didn't need to do that. Here we go. So for square root on Excel, we raise to the 1/2 power. That's a whole nother story. If you remember from exponents, square root is the same as being raised to the 1/2 power. So that's how we tell Excel to do a square root. So we'll say equals, and we'll start our parenthesis, and we'll end it with to the 1/2 power, okay? On top, we've got this 96.001 divided by 8, close, raised to the 1/2. And I'm putting the 1/2 in parentheses also to make sure it does it correctly. And that gives us our answer there. We got 3.5, but closer would be 3.46. So that finally concludes this section. I promise you the last two are not this long.